All right, let's talk about how to get visual transformers in shape, scaling laws for compute optimal model design. I really like this paper because it is one of those papers that takes something that is difficult to do or compute intensive to do and finds a way to do the same thing cheaper. And this kind of thing happens a lot where someone comes up with a way to do something that works, even works really well, but is pretty expensive. And then once we have something that works, we can optimize that and get the same sort of performance or the same quality with less cost, in this case, less computational cost. And that's exactly what I did here. So up until this paper, there was this perception that when you're scaling transformer networks, when you want to get better results out of transformer networks, you have to scale them by increasing the number of parameters. So the more parameters you have, the bigger your network, the better your model is going to be. But of course, the more expensive it is to train. And there are lots of papers about the scaling laws. Chinchilla is the most famous one, where they figured out how the quality scales with model size and therefore with more computation. But here they're arguing that this is not the whole picture, that looking at just the parameter count is kind of a low resolution view and you're losing a bunch of information, and it is better, or you can get better results, specifically in vision, but also in some other tasks, if you scale smartly. Depending on which dimension you scale, you'll get different results. So here they look at 3 different dimensions. So it's a visual transformer. So transformers have, encoders and then the MLP component. And so they look at these 3 dimensions. So the number of encoders, so the depth of the network, how wide the network is, and then also the size of the MLP at the end. So they scale these 3 different things independently and figure out some rules about how each of those should be scaled relative to the others so that you get optimal performance for your compute budget. And that's another thing they kind of do. I mean, it's not like super groundbreaking, but makes sense. They say that, rather than just looking at a function of compute budget, you say, okay, I have this compute budget. What's the best I can do with this? Because if you have a big model and you don't have enough compute budget to train it, your model will be undertrained and you'll get pretty poor results. If you use the same compute budget but with a small network that such that you can train your network enough, you'll get better results than under training. So they look at that and they find some rules. So this is basically the formula that describes how this how they come up with it, and they find different factors that tell them how to scale each of those 3 dimensions, depth, width, and MLP dimension, so that their model comes out optimal. And then they prove that it works by doing a bunch of benchmarks. So let's just go to that, evaluations. And they show that, so these are the 3 different scores, and ViT is the model they introduced. So shape optimized visual transformer. And you can see that it's got like 400 million parameters, and it has comparable performance to, for example, this one, ViT G14, or even this one, the 2 billion parameters and pretty similar performance. And they do it in a bunch of ways as well, linear probing. And the other interesting thing they find is that this kind of these specific scaling factors between the different dimensions apply almost regardless of task kind. So whether you're training for classification or captioning or VQA, the relative scaling of different dimensions stays basically the same. One exception to this is this panoptic segmentation, which they say that our results indicate dense segmentation task can be a limitation of the proposed optimal model, and a different model chain might be derived from this domain. So, it goes pretty far, but it's possible that for some specific tasks, you might want to use different way of scaling your transformer network. So this is it. Pretty cool to get a smaller model doing the same thing and also find some general rules for how these things can be scaled. Thanks so much.